Okay, so I want to even show you how we're going to even use this formula using projectiles. Okay. A ball with a mass of 0.5 kilograms is projected vertically downwards towards the ground from a height of 1.8 meters at a velocity of 2 meters per second. The position time graph from the motion of the ball is shown below. So there you can see, okay, they're measuring it and saying it was 1.8 meters above the ground. Okay, it is thrown downwards. After a certain time, it reaches the ground at T1. Okay, and they don't say it on the graph obviously because it's position versus time, but initial velocity was 2 meters per second. So if I want to use this formula, I have to start with a force diagram. Awesome thing about these are there's my point. What force do I first draw in? Weight, which is always just down. Okay, and they don't say that, but I suspect we can ignore friction. Okay, so these questions we usually have no worries of friction, but this is weight. In which direction is the ball going?
Down.
It's downwards, so this is also my direction of displacement. Okay, so that is my direction of displacement. And what is my displacement? 1.8. Excellent. Meters. 1.8 meters. Now what's nice about this formula is you don't have to do sign. You don't have to choose up or down as positive or negative. Okay, because that's already included in the angles that we're going to use. The angle is going to do all the work for us. Okay, so if this is my direction of displacement, okay, there's no other forces acting on it. Okay, there's no friction, there's no surface, so there's no normal force, there's no applied force. This thing is a free fall. There's only weight acting on it, which is absolutely excellent because now my net work done is equal to work applied, which doesn't exist, plus work done by gravity, okay, plus work done by friction. These two don't exist. Okay, now for net work, what am I going to use? Change in kinetic energy, which we said is a half mass future velocity minus initial velocity. Okay, net force times displacement, or mass acceleration delta x. Oh well, I suppose let's look at what question we should answer. They say, what is the maximum vertical height reached by the ball after the second bounce? So here's the 1, 2, 0.5. You agree? Okay, so we've answered that question. Okay, calculate the magnitude of the time indicated on the graph. So we want time. Okay.
I think acceleration, yeah, the mass acceleration one will do.
Okay, well let's see on this side of the equation what do we have. Okay, here we have mass times gravity times delta x times now gravity. The angle that gravity makes with displacement is 0. So this is just cos of 0. So look, if I use this formula, I just have mass acceleration is the gravitational acceleration. So I just have mass times delta x. I know that. Okay, do you see? So that's not going to work to use this one. But you're right, it is correct, but it's already on the right hand side. Okay, so we'll use this one.
Yeah, I wanted to also ask about the acceleration.
Yeah.
Can't you equate it to, what is this, velocity over time?
Change in velocity over time.
Yeah.
Yeah, of course.
So
yeah, okay, so you want to use that maybe. So we'll say mass is future velocity minus initial velocity over delta t, okay, like that, times delta x.
That's what I was thinking.
Okay. Let's just see. I think it might work. I've got the masses is going to cancel. Delta x is going to cancel. Gravity is equal to future velocity minus initial velocity over time, where my I know my initial velocity, I don't know my future velocity. I have 9.8 here, and I want time and future velocity. I'll have to calculate both of those. Okay, so okay, maybe I can use it, but I still need future velocity. Okay, and you are indeed correct. That is first what we are going to have to calculate. We first need future velocity before we can get time. Okay, is there another formula? Again, I'm not trying to show you how to answer this question. There's different ways of answering. I'm trying to show you that with the same formula, you can answer this question. So going in this direction that you just did, using this mass acceleration delta x, you would have gotten to the point and you said, I need future velocity. But look here, here's a formula that's going to give me future velocity. And then we can use exactly what you said. Okay, so I have a half times mass times velocity, future velocity squared, minus initial velocity squared. Okay, the mass is going to cancel on both sides. And again, mass doesn't have any effect when it comes to free fall. And here we can see it again. Multiply 2 on both sides. So I've get future velocity squared minus initial velocity. So I'm going to add the initial velocity on the other side. So what do I get? Initial velocity squared plus, and remember I multiplied the 2 on this side, 2g delta x. You see, how beautiful is that? It's an equation of motion. You don't even need to go and worry about it. They don't even need to give you a formula sheet. You just need to get this. Okay, so initial velocity we know was 2, 9,8, delta x is 1,8. So future velocity is the square root of that answer. Will you quickly calculate it for me, please? Okay, so we've got 6.11 meters per second. Now again, you can see I never chose any directions. What is important now is that I do say this is downwards. Okay, that's not what they asked though. We still need to calculate the time. But now we can use that formula that you suggested, where we said the change is now 6.11 minus 2 meters over time is equal to 9,8. And then what do we get? So you simply divide 6.11 minus 2, divide that with 9.8.
.42.
0.42 seconds. Okay, awesome. Okay, here we go again. Okay, we must calculate the velocity with which the ball rebounds from the ground during the first bounce. So what I just want to show you is that what you should remember is that these you should consider as two completely separate events. They've got absolutely nothing to do with each other. They do really, because he reaches with a certain velocity and he bounces back with a percentage of that velocity. Okay, the ground absorbs some sort of velocity. So if I reach the ground at a higher velocity, I would bounce back higher. But treat it as a separate thing. Don't use anything from this question in your next question. So if I just assumed that this was a vertically projection upwards, what can you tell me about this upward projection?
That the only force applying on it is still gravity.
Excellent. So I'm going to, again, I just want to show you the use of this formula. We've got our gravity is the only force acting in on it. Okay, so the system is exactly the same. Change in kinetic energy is equal to the work done by gravity. Okay, because there's no applied force. Yes, there is an applied force here, once I touch the ground, yes, now the ground is applying a force, but during my motion, as I'm moving, there's no force except for gravity. That's the important part. The only time there's a work applied is if there's literally a string attached to me the whole time with a force on it. And that's not the case here. So again, I'm going to use this half mass times future velocity squared minus initial velocity squared is equal to work done by gravity is mass times gravity times delta x. Okay, same thing I had here. Okay, and again the angle between, oh wait a minute, okay, which is my direction of motion? Upwards. So what is the angle between my
180?
So this must be cos of 180. And that, you see, I don't choose a direction as positive or negative. The angle does it for me. Okay, so let's go and work this out. So now what we have is, what do we know about these values? Again, masses will cancel. We don't need mass. We'll cancel on both sides. Okay, so again, I'm going to have this formula that I had before. Vf squared is equal to Vi squared minus, because of the cos, okay, 9.8 times 2, which comes from that half multiplying to the other side, times delta x. Okay, so do I know future velocity or initial velocity?
You don't have either of them, but you have delta x.
Do you have delta x? What is delta x?
0.9.
0.9. In other words, you are telling me that from the bottom to the top is 0.9 meters. I agree with you. We have that this is negative 9.8 times 2 times 0.9. But you do have the velocity at the top.
Oh, yeah.
What's the velocity at the top?
0.
It's 0 squared is initial velocity squared. Now look, if you didn't have this would have been a positive. And when you take the positive to the other side, it would become negative. And now you have something squared equal to a negative. Okay, that would have been, your calculator would have given you an error and you had to, okay, so we have initial velocity is the square root of that thing. So what do we get? Initial velocity, please? Exactly.
Yeah.
4.2 exactly. Wow. Okay, so 4.2 meters per second, and direction is?
Upwards.
Upwards. Okay. The ball is in contact with the ground for 0.2 seconds during the first bounce. Okay. So there's the first bound for 0.2 seconds. Calculate the magnitude of the force exerted by the ground on the ball during the bounce if the ball strikes the ground at 6.27 meters per second. Okay, so during the, so I don't know if we calculated it wrong, okay, but they tell us that it should be that, but that's okay, it doesn't matter. I'm sure we did it. Okay, so okay, and this question is very often asked. As soon as you have contact with a surface and it bouncing back, so actually the wrong way, so I've got something coming in and then bouncing back, it means what actually happened here is that the momentum changed. Momentum used to be downwards, now it is in the opposite direction. Okay, and momentum can only change. We have a law that says, or a principle that says that momentum is conserved in an isolated system. So momentum doesn't change unless what?
An external force.
Exactly. So there's now an external force, and how and what is the relationship between this external force? Okay, that means there's a resultant force. It's the change in momentum or the impulse over time. And that's what we need to calculate. Impulse is mass times the change in velocity. So future velocity minus initial velocity over time. Okay, so here we can't use the formula. Well, maybe we can if we use the same formula. The problem is, I suppose, let's try it. Okay, we have that the net force is the net work done. This time I'm just on the surface. Okay. Work done by gravity. You have applied work. That's the work done by the ground, plus the work done by gravity, plus the thing is it doesn't move. While it's on the ground, it doesn't move at all. So there's no displacement. So I don't think this formula will work. Okay, so let's just go back to this method. Okay, mass we have 0.5. Okay, and now here's where the problem comes in. Okay, future velocity is the velocity upwards. Initial velocity is the velocity downwards. And Carl, I can almost promise you will have a question like this. Okay. These velocities are in opposite direction, which means they should have opposite signs. So if I say my future velocity, that's the velocity with which it bounces back. We said that is 4.2. If I say this is 4.2, it means I chose this to be positive, which means downward must be negative. So this one will be negative, negative. It's already a negative there, but this one is also negative. Do you understand?
Yeah.
Okay, so this one will become plus 6.27, they say, divided by 0.2. And now you've calculated it, and when you calculate it, you have your net force. So I just want to show you that you will definitely have, well, I'm convinced, I see it almost in every exam, where you have to calculate this force that something that a surface has that bounces something off of it, and students just always substitute this with 4.2 minus that with 6.27, and you'll see then you get something like 2,07, negative 2,07, while in fact this answer here is 10.47. You see, that's a massive difference, because if I don't change the sign, what I'm actually saying is it reaches the ground at 4.2, but it's still going further. It reaches the ground at 4.2, it reaches the ground at 6.27, but then it's still continuing down, and but its velocity ends up being 4.62. So all the ground did was to slow it down. You see, it didn't bounce it back. So obviously the force needed to slow something down is less than the force needed to change direction. You can imagine a car driving towards you. The force that you need in order to slow down that car is less than the force you need to actually hit it back. Okay, so just keep that in mind. That's often asked, and I'll stop this question there.